All right, welcome everyone to our next seminar. Today I'm delighted to introduce Anais Möller, who's coming to us from Swinburne University, where she is a DECRA fellow. So Anais is more on the astro side, but is working on something that I think most of us will be very interested in, probing the dark universe using transients. So this is an exciting area of research, and yeah, I'm very glad to have this as in our seminar schedule. So. Anais, I'll pass it to you, and you can take it away. So thanks very much.
Thank you very much for having me. Before I start telling you about how we can use transients to illuminate the dark universe and the fundamental components of our universe, I would like to acknowledge the traditional owners of the land where I'm standing, the Wurundjeri people of the Kulin Nation. And I believe some of you may be in the land of the Gadigal people of the Ora Nation. And wherever you are standing right now, I would like to acknowledge the traditional owners and custodians. So today I'm going to tell you about transients and their role on understanding the components of our universe, in particular the effect of dark energy. But I'm also going to mention how we can use these transients to understand extreme physics and that we cannot access here on Earth. And this is mostly work that I do also in OSCRAF, where I'm an AI. So let's start with transients. For those who haven't heard about the term, we basically call transients astrophysical events that happen momentarily, with quotes, in time. And they can be, for example, a white dwarf accreting material from a companion star, and at one point it would explode. This is what we call a type 1a supernova, and they shine brightly for a couple of weeks and then fade away. So the type 1a supernova, that explosion, we call it a transient. Here I'm showing you a video of two neutron stars, and they're gonna merge, and you can see the gravitational wave signal from that merger. And when they merge, they also produce an optical transient that we call a kilonova. Actually, it's a multi-wavelength transient. And of course, it produces a gravitational wave signal as well. So basically, transients are astrophysical events that are quite extreme, happen usually is the death or the newborn of a star, let's put it that way, rebirth, and happen for a couple of weeks, fade away, and it's gone. So why do we care about transients? So part one is because they are responsible of most of the chemical enrichment in our universe. Here I'm highlighting in red the three types of mergers or explosions, type 1a supernova, core collapse supernova, and kilonova. And if you see the periodic table of elements found here on Earth, you can see that most of the elements actually can be traced back to an origin in one of the extreme events. Transients are also very important for galaxy evolution. So this is a simulation of a galaxy and the chemical enrichment and turbulence of gas. And what you're seeing here is in very large time scale. So we're talking about mega years, supernova explosions and other things that move gas around. But what my main expertise is to use transients for cosmology. So I use exploding stars called type 1a supernova that I'm showing here the video of one exploding, shining brightly, sometimes shining brighter than millions of stars in a galaxy. It shines for a couple of weeks and fades away. So there are many types of supernova, but type 1a are quite interesting because they have homogeneous spectral and photometric properties, which is a fancy way of saying that we can standardize the brightness where it shines in rest frame, and we can use them as light bulbs around our universe to measure distances. So this is a way that we measure usually the cosmic expansion. So we cannot go up there and measure distances with meters because it's way too far away. We use type 1a supernova as standardizable candles to measure how the universe is expanding and thus derive the components of our universe. So in the last years, we have had like 2 decades of using type 1a supernova as these measurement tools. And in the 1990s, we have two groups that actually won the Nobel Prize for measuring that cosmic expansion and finding that we were expanding in accelerated fashion, which is evidence of dark energy. They also measured at that time that the universe was flat with these measurements. And this is the late 1990s. Now, this is the first generation experiments with type 1a supernova. Second generation experiments like SNLS or SDSS, as now, well, we know that the universe is expanding in accelerated fashion, but can we constrain the physics, that dark energy that we're trying to explain the expansion with, and whether it's a cosmological constant or not? And then third generation experiments, which I'm going to present some of the results today. Well, we started in the 2010s. Our final results have been published actually January this year, and we're very proud about it. And here we're entering into a phase of precision cosmology. We're really trying to target whether we can explain dark energy as a constant or is it evolving with time, and also looking a little bit beyond. We have had 2 decades of experiments of type 1a supernova, and we're expecting the Vera C Rubin Observatory not only to find hundreds or thousands of type 1a supernova, but millions. And this is a shift in paradigm. And I'm going to tell you a little bit of how we're thinking to move towards Rubin and what type of measurements we're going to be able to do with supernova. So let's start with the dark energy survey. So the Dark Energy Survey was a 5-year supernova survey. Well, of course, we have other probes for measuring the effect of dark energy in our universe, but today I'm going to concentrate in this supernova survey. So it's 5 years, and we expected to discover around 2,300 type 1a supernova, well sampled with good measurements for cosmology. Now, we're not searching supernova in this beautiful galaxy that is in NGC 253, but what we're searching for is supernova exploding in this galaxy, and right now, a type 1a supernova just exploded. So now you're going to tell me, okay, this galaxy, very pixelized, very far away. With those couple of pixels that we have, we actually monitor the brightness evolution over time of that supernova. It's an explosion that rises in luminosity and fades away. We use 4 band passes or 4 broad wavelength ranges to measure that brightness evolution. So it's GRIZ, which is basically is the optical to the near infrared. So this is what the Dark Energy Survey measured. Now, in Australia, we did a program called OSDES, and we obtained over 100 nights at the AAT using the 2DF instrument and A omega. And what we did with OSDES was to get the spectra of the host galaxy and the spectra of the supernova if they were shining, because of course they fade away, so you need to get them around maximum light. By getting the spectra we got from the host galaxy, the redshift, and also some of the properties of the host galaxies, and from the spectra from the supernova, we get a classification, whether it's a type 1a or not a type 1a. So these can be many types of core collapse, 1Bs, 1Cs, 2Ps, 2N, etc. What we want is 1As because they are the ones that we can standardize for cosmology. The other ones we cannot. Some of them can be kind of, but the precision is not great and it's very hard. So we're going to center ourselves in type 1a supernova. Now, I told you that the Dark Energy Survey did a 5-year survey. But for the first 3 years of the data, we decided to do a first analysis of the data. So what we did is we took our supernova, the ones that we classify using the spectra to know whether it's a type 1a or not, and we obtained 400 type 1a supernova. And we expect the contamination for this sample around less than 2%. These 400 type 1a supernova, we use them to measure how the universe was expanding. And this is what we call a Hubble diagram. So it's basically the luminosity, which is the luminosity distance, or distance modulus, we call it, which is a function of the luminosity distance as a function of redshift. And in all of these yellow and red points, that's a type 1a supernova. Now, the red ones are from the dark energy survey. The yellow ones are a sample of low redshift close by supernova. And then with that data, we compare how we measure that evolution of distance modulus against redshift with models, cosmological models. So whether we have a universe with only dark matter, how much percentage, do we need dark energy? Of course, the results show that we actually need dark energy to explain the measurements that we have. We have been measuring this for a while already. And then what's interesting about the dark energy survey is not only we know that we need dark energy in our models, we're really measuring whether that's a constant or not. So the type of constraints that we do are in green here. On the left, you have the density of dark energy against the matter one. And on the right plot, we have something called W that I'll tell you in a second what it is against omega matter. Now, the green contours are the constraints from type 1a supernova, and in yellow, you're seeing the CMB constraints. And they're actually quite complementary, quite orthogonal. So combining them gives us really big power of constraining the percentage of dark energy and dark matter. And you can say that we are in a very, what I call vanilla model. So it's around 67% dark energy, 30% dark matter. And now in the plot to the right, we're measuring W. So what is W? W is the equation of state of dark energy. If it's -1, it's a cosmological constant. And you can see that we are actually quite in agreement with a cosmological constant in these results. Now, this was in 2019, so some years ago. And to do the 5-year analysis for the dark energy survey, what we wanted is to see how can we take this analysis further. So I'm going to split my talk in different parts. So we have the standardization, which is the y-axis in the yellow. In purple, the measurements of redshifts. And in green is detecting and classifying type 1a supernova. And why I divided like this is because when we did our analysis, we were systematically limited. So this is our uncertainty budget in the constraints that we obtain. And you can see statistical errors are actually quite low. Systematics are really dominating. And these are the ones that we really want to lower for our analysis for the whole dark energy survey sample, but also for Rubin LSST. And you can see that we have different families. One is the low redshift sample. The other one is selection effects and understanding the populations. Standardization is understanding the properties of the type 1a supernova and their environments. And of course, measuring redshifts requires some corrections. I'm going to tell you mostly about the green and the yellow, so classification and standardization today. But if you have any questions, I'm more than happy to answer about the other regimes. So classification. So I told you that we're classifying type 1a supernova, getting the spectra around maximum light of that explosion. But an alternative to that can diminish selection effects because selection effects are because we don't have telescope time that is infinite, there is weather, you need to get them bright enough or in the good time lapse to actually get the spectrum. So there is an option of automatic classification, which is basically using that brightness evolution over time, which I call a light curve, to actually classify whether it's a type 1a or not. So this means it's partial information. The spectra gives you the all wavelengths of colors, or at least a more thorough picture of it. But photometry is easier, cheaper to get, and we get it for all the detections of the dark energy survey. And we are worried, of course, that the contamination is higher if we're classifying with light curves and maybe biasing the samples. So in 2020, I developed an algorithm that is called supernova. And then it's because it's a neural network, it's a deep learning framework. It's actually open source. You can download it and use it for your science case. And I implemented recurrent neural networks to classify light curves. So basically, you input brightness evolution over time in a filter range, so it's time series. And if you train the algorithm, you can classify and obtain a probability of this light curve being a type 1a supernova at any time step. So this algorithm, I created it to have a special emphasis on accuracy because we want very good classification, pure samples, and statistically robust classifications because we want to do precision cosmology with it. And of course, I trained it, got very good performance with the simulations. But a couple of years later, Maria Vincenzi, which was then working in the UK as a student, started leading a project that I would call it Let's Try to Break Supernova, which is basically try to change how we train the classifier and how we evaluate it with these variant simulations. Different templates of core collapse supernova, different templates of type 1a, different rates, different models, etc. And what you're seeing in this plot is the contamination as a function of redshift for the different supernova models, which are all in red and in yellow, and other types of classification in purple and blue. And you can see that we really can constrain the contamination very, very low. And we don't have that many changes on it, even if we change the templates and the rates of the training set. So this was pretty promising. We actually got purity of 98 point something percent. So it's equivalent to spectroscopic classification. So now with this knowledge, we went and I developed a whole set of analysis methods to actually get the light curves from the dark energy survey, apply supernova using the light curves and their host galaxy redshift that we obtained, for example, from OSDES, and we classified the events. And you can see here some of the events that we detected. And this is the 5-year sample. So we have 1,400 type 1a supernova. So we're talking about 3 times more supernova when compared with the spectroscopic classification. So what I'm showing you here is an histogram of the redshift distribution for the spectroscopic sample in maroon and in yellow, the photometric sample. So you can see that we are actually having much more events. We are going much deeper in redshift, which is very important for us because really the constraints that we want less selection effects, a higher redshift. So with that, we did a Hubble diagram and we published the results earlier this year. And here the Hubble diagram is a little bit different. We have changed the way that we are doing this analysis. Now, instead of making a cut on the probability, let's say 90% probability of being a type 1a, I put it in the Hubble diagram. Now we're using the probabilities as a weight for the analysis, and that's what you see in the bar in the right. So the probability from supernova in clear blue to dark blue, 1 being type 1a supernova for sure, and 0 being, I'm pretty sure this is a core collapse supernova. And you can see how it populates our Hubble diagram. Now, the other thing that changed is that we are now really precise in our analysis, and we can compare not only a cosmological constant as dark energy, but also dark energy that is evolving with cosmic time that you can see here in a green line, while lambda CDM is a purple line. And you can see that they are quite close to each other. So that means that really we need a precise analysis and good type 1a supernova measurements to constrain these. So if we do the plot again, W, the equation of the state against omega matter, you can see that we are 2 sigma consistent with a cosmological constant, but we're seeing that there is a little bit tension away from this -1 value that will be a cosmological constant. Now, if we go to a model where W is changing with cosmic time, which is this parameterized by WA, so A being the scale factor, you can see that we are actually not in WA0. We are actually with the tension actually to have a WA which is negative, which would mean, and this is still not a 5 sigma result, so it's hints only, that there are hints that dark energy could be explained with a model where it evolves with cosmic time. Now, we published this earlier in January. A couple of months later, the DESI survey with BAO measurements actually found also some hints of this. We have combined the data. There's a lot of discussion right now trying to figure out if we can disentangle these. And Rubin will be a great opportunity to actually pinpoint and have this really discovery. Now, I'm going to tell you about what is limiting us and how we can go for Rubin. One of the things that we are very proud of is that we are now systematics we have it controlled. So this plot is very complicated, but what you want to know is statistics, uncertainties by statistical errors is in white, and all the colors are the systematics that we have been reducing. So we're super proud about this because it's a new era. But also, if you see in green, that's the classification systematics. And you can see that it's really much smaller than other systematics, in particular the yellow and orange, which are the standardization, the properties, and the environments of type 1a supernova. So right now, our main focus is trying to understand these systematics to actually take our analysis to the next step. And this is what I'm going to talk about, is how can we use the dark energy survey data to understand properties and environments of type 1a supernova and thus improve our standardization. So when I showed you this image or this video before, I told you, okay, we have a white dwarf. This is a carbon oxygen white dwarf, accreting material from a companion star. And I didn't say anything else, except that at one point, it will explode because it reaches a limit. So we believe that that limit was 1.4 solar masses, which is a Chandrasekhar mass. But we have now evidence that it could be sub-Chandrasekhar or super Chandrasekhar. I have also didn't tell you that actually carbon oxygen white dwarf we know, but we don't know what the companion star is, whether it's a double degenerate, which means another carbon oxygen white dwarf, or it's a main sequence star or a red giant, and we have hints for different ones of them. So if we cannot understand where type 1a supernova come from, our standardization may be missing pieces. And this is part of the things that we're trying to solve right now. And the emphasis here is how do we take these large samples that give us these population properties to get better models and understand what's going on. So when I told you about standardization, I told you that type 1a supernova are standardizable candles. If they were standard candles, when we measure the distance modulus, we will be just comparing the observed magnitude with the absolute magnitude. But type 1a supernova are not standard candles. They can be corrected to become standard, so it's a standardizable. And this is a current corrections that we have. So I'm going to tell you a little bit more about them. So MB is the absolute magnitude, the CAPS MB. X1 is basically the stretch of the light curve. C is the color of the light curve. And alpha, beta, and gamma are constants that depend on the sample. And these X1 and C corrections is what we call the trip relation. It actually is how in the 1990s type 1a supernova were standardized. Now, earlier 2000s, we found a correlation with host galaxy masses. And we still don't know where it comes from, but we're trying to figure that out because this is a big part of our standardization problems. And then selection effects is always a problem because of course, if you go to higher redshifts and fainter, like a fainter supernova may not be selected compared with brighter supernova. So you need to take into account this. So I'm going to tell you a little bit about selection effects, properties, and environment, thinking towards Rubin, thinking towards what can we do with the dark energy survey to improve this. So one of the questions I had with the dark energy survey is, okay, we're supposed to detect 2,300 type 1a supernova. Spectroscopically, we have around 400. If we use the cosmology sample that uses the host galaxy redshift, we have around 1,400 type 1a supernova. Where are the rest? So I did a paper earlier this year about making this classification without any information from the host, because sometimes we don't have the host redshift. Sometimes we cannot even see the host. They are so faint. So 4% of these supernova are considered hostless because we couldn't detect the host galaxy. And you can see that we're really going to fainter magnitudes of the supernova, parameterized by the peak magnitude in the I band. And you can see that the magnitude of the host galaxies are really going fainter. So we're missing a lot of those faint hosts in our cosmology analysis. And this is super useful because then we can try to understand if our models, which are our simulations that you see here in gray with the maroon line, match the data we have. And this is an evolution of color and stretch as a function of redshift. And you can see our simulations are pretty good or mimicking the data, but there's a couple of places of tension. So this is something that we are looking to improve now. The other question that we're trying to understand is this mass step. The mass step is basically a correlation between the Hubble residual, or basically a difference in brightness, between those type 1a supernovas that live at galaxies that are low mass towards high mass. But we don't know what this is. So some people say it's progenitor channel, so which type of stars we have. Some people say it's dust. Some people talk about selection effects. So I took the sample I just showed you where we are really getting 2,300 type 1a supernova, which we show here in green. And we tried to compare if we could see that mass step. And here is parameterized as a function of stretch and mass step. The mass step is around 10 here, so there is a vertical line. And you can see that the cosmology sample in orange has a higher mass step than the sample in green. So part of the mass step could be potentially explained with selection effects. We have also been doing other things, like, for example, this is work by Mitchell Dixon that just got his PhD here at Swinburne. And he actually took the spectrum of the host galaxy and tried to find correlations between the mass step and properties of the host galaxy, like stellar age, metallicity, O3. And you can see that there are some indicators that are a little bit stronger than others, but not the smoking gun yet. And we also did tests trying to explain with dust by using one of the markers that is H gamma over H beta, and we couldn't find really strong conclusions on this. So this is the thing that right now all supernova cosmologists are working on. I have a student here working with this because it's super interesting to try to understand how can we standardize better type 1a supernova and how can we really constrain what the progenitor system is. So this is a dark energy survey, and I have shown you till now results of a survey that has been online already and has finished. But now I'm going to switch the view towards the future. So the Vera C Rubin Observatory is coming online next year. Actually, first light will be in a couple of months. It's pretty exciting. What is the Rubin Observatory? So the observatory is in Chile. Basically, we have a telescope of 8-meter diameter and with the world's largest CCD camera, excellent resolution, and we will be imaging the sky from the 300 to 1,000 nanometer bands. Every time the telescope images the sky, the southern sky, it will gather an area of 9.6 square degrees. This is equivalent roughly to 40 full moons. So this is amazing. So this is another era of big data in astronomical surveys, especially in optical. For people that work in radio, of course, you gather a lot of data, but for optical people like me, we're really entering into a new era. So Rubin will do for the first 10 years a dedicated survey called the Legacy Survey of Space and Time, so LSST. It's starting mid-2025, next year. And what it will do, it will be doing a video of the southern sky over these 10 years. So we expect to have between hundreds to thousands of visits of the patches in the southern sky. And you can see here the hundreds in purple and in yellow, the thousands of visits. Those thousands of visits that are the deep drilling fields, these are very deep fields that we will target every couple of days. So we will get a very good video of the southern sky, excellent for transients. also very deep. In a single exposure, we will get from 23 to 24 magnitude limits. So if you can see an image from, for example, SDSS, and you scale it to what LSST will be, this is how much more sources we will be having. So this is amazing. Now, Rubin is a new generation, and we have very different data products. So, of course, we have raw data, catalogs, annual releases, and I encourage you to join the Rubin effort here in Australia. We have a LEAF grant, and we have PIs that have data access to the proprietary data. But I'm going to talk today about a public stream, a public data that is called the prompt data product. So basically what we will get publicly will be the difference between a new image, an old image that we call a template, and that difference makes a blob if something is changing, and that monitor of that blob as a brightness evolution over time or a light curve. So this is basically capturing all that is transients and variables. So this can be from Type 1a supernova explosion to variable stars, flaring stars, satellites, asteroids, etc. Now, we expect up to 10 million detections every night in this prompt data product, which means basically that we will have so many changing events from LSST that if you want to do your science, you're basically, how do I disentangle my Type 1a supernova detected tonight from the million events that were detected tonight? And this is where the brokers come in. The brokers are basically infrastructure and collaborations that have been granted data access, also because you cannot communicate terabytes of data every night to everybody because we don't have the storage and it's very complicated. So 7 groups around the world has been selected to receive these. And the brokers are the tools that can help us find these answers to these questions of the extreme physics of transients and dark energy because we can pinpoint the most interesting objects. And that's where Fink comes by. If you have met me or you have seen my cup, the Fink collaboration, I founded it with Emily Ishida and Julien Peloton in 2019. It's a broad science collaboration. We have been selected to be one of the official Rubin brokers. So for the next 10 years, we will have access to this data. And right now we have grown to 70 members in 14 countries. The question that everybody asks me is always, what does it stand for? It's not an acronym. Fink is just its name. We like the name and it's there. So how does it work? We have 7 brokers around the world that will receive the same data, but each of us has a different community, a different way of processing the data. And today I'm going to tell you, of course, about Fink. We are deployed in France, in the supercomputer center in France, in Lyon, supported by CNRS. And of course, I'm one of the PIs, so there is a strong Australian component here. So 2 months ago, we did a test with LSST where they used simulated data and send it from the telescope to the US to process it and send it to the brokers. And that's called the operation rehearsal. We got 9 million simulated detections and we tested all our infrastructure and we're ready to process Rubin. And even before LSST starts, which is mid next year, we will get first data from the telescope while testing everything around March, April next year, probably. So it's really exciting times. And now I'm going to take what's the rest of my talk to tell you about how we do this and how we can actually use Fink to do science. So the first thing is, well, Fink is data access to these millions of measurements of transients and variables per night for a decade. And you can also understand how your targets are selected, because the idea is that we get that data and then we can split it up in different science cases, whether it's asteroids, satellites, accreting stars, black holes, AGNs, supernova. So how does this work? We basically get the stream, and right now we're deployed with CTF, which is a precursor of LSST. We do first a cross-match with catalogs to see if this object is a known variable star, it's close by a galaxy, or we don't have any information whatsoever. Then we also cross-match with dynamic catalogs and VOE events and GCN notices like footprints of gravitational wave, neutrinos, gamma rays, etc. Then we take all that information and we also give it scores of these events being potentially a supernova, a kilonova, a microlensing event. So you can use all those scores to actually select your object, and this is all community driven. And then you can do your customizable filtering. I want transients that are close by a galaxy, that are blue, and they have a probability of being a type 1a supernova by this much. And then you can access it. And there are two ways of accessing it. One of them is like the human-friendly one, which is our web portal, for example, finkportal.org. You can go right now and see some of the images and likers that we get from the Zwicky Transit Facility, precursor for LSST, and how we classify them. You can also use it to query our database through a REST API, which is basically a fancy way of saying you go to your code or your Python notebook or your terminal and you say, I want this, and 2 lines of code later or 3, you have the data in your computer. And the other way of having the data is like what we call real time, which is within minutes of the detection, you can actually receive an automated stream with your selection that can trigger follow-up, for example, in different telescopes around the world. So this is how you can create the selection of your targets. Of course, you can do all these of posteriori, but the power of transient science is actually reacting fast. And within a day or 2 or minutes, depending on your science cases, you can do your research. So Fink is not only me and Supernova, it's a community. So here I'm showing you some of the pictures of the events we have done in France, in Switzerland, in Australia, and recently in Brazil. And it's community driven, so everybody can join. We are 100% public data, public code, so everything we do is very transparent, and you don't need proprietary data access to access Fink. Of course, we do very different science cases, and I cannot tell you about all of them. Of course, supernova is a big part of what we do. But we also do nuclear transients, solar systems, like asteroids, finding the weirdest thing, anomalies, kilonova, gamma ray bursts. We have a partnership with SWOM, which is a French-Chinese mission of gamma rays in space. It's already a satellite in space. We also have a partnership with Euclid to get the solar system detections. And of course, there's much more. And we want to populate as many science cases as possible. So if you're interested in using this data, please let me know. I'm more than happy to talk about how we can do science. So I'm gonna finish my talk talking about how can we maximize science for the topics I am most interested on, which is, for example, type 1a supernova cosmology, basically constraining what dark energy is. So this is work that I'm doing with the Dark Energy Science Collaboration and Fink. The first thing to know is that machine learning classification for supernova is becoming a standard. On the left, I'm showing you the dark energy survey Hubble diagram, but not only in dark energy survey, we're using supernova, we're using it also, well, other people have used it for SDSS and pan-stars data. We have tested these machine learning classifications with simulations of LSST. So we have on the left a confusion matrix of the classification of supernova versus other things. And you can see that we can actually get good accuracy with LSST simulations. We also have tested what type of rate we would recover with type 1a supernova photometrically classified with LSST. And something I'm working right now is using this precursor data from CTF. And here is a light curve of CTF, so it only has 2 band passes, G and R. And we, of course, we classify with different machine learning models. So here we're showing 3 models, actually, in orange, blue, and clear blue. And one of the things that we really don't know is how to model type 1a supernova very, very early. So when the brightness evolution is rising, and that means much less data. Okay, it means 3 points of data. So how can you identify if this is a type 1a supernova, and how can you get more data to improve the models to explain how the explosion is rising? So we have implemented a stream that basically reports automatically all of the type 1a supernova candidates to the transient name server, which is the International Astronomical Union mechanism to report them. And we're also sending these candidates to DIVAS, which is a project that we have at the ANU 2.3 meter to get very early type 1a supernova. We have been quite successful in identifying early type 1a supernova, even with so little data. So in dark blue, you see all of the things that have been reported that have been classified as type 1a supernova. In orange are the peculiar type 1a supernova, the ones that are not really normal. And in gray and other colors are other types of supernova. So you can see we're pretty good at this. The other thing that we're working is a little bit beyond supernova. And this is something I'm doing with OSCRAV and the Transient Variable Star Science collaboration, that is to get large samples of transients to understand their mechanisms and progenitors. And this is like a very cartoonish map of the brightness against decline time of different types of transients. And you can imagine that these are not squares or circles. We really don't know the boundaries of these families. And there are some of them that we really don't know what they are, like ambiguous nuclear transients, rapidly evolving transients. We really don't understand what they are. And these are some of the students I work with that are working in trying to understand these classes, whether it's with CTF data or other precursor data. Of course, the power of Rubin can be enhanced if we join it with other wavelengths. So you can see here that we can take it from the radio to gamma ray. And this is something that with Fink we have been working on. For example, I'm part of the VAST collaboration in ASCAP, and we're trying to understand what type of transients shine in the radio and in the optical and characterizing them. We're also trying to trigger follow-up automatically from Siding Spring Observatory with a leaf grant to construct the robotic telescope network in Siding Spring, connecting it with Fink and other surveys. We also have partnerships with space telescopes, etc. Why are we thinking that this will be immensely good for science? Because we know that joining multi-wavelength data can help us understand better the astrophysical objects and the physics. And the canonical example is 170817, the gravitational wave detection, where it was followed by a gamma ray burst. And then we found in the optical a kilonova. And on the left, we're showing SkyMapper images. At that time, I was actually working in Australia with SkyMapper, and we took those images. And this data has given us a lot of information of the chemical processes and the physics of that kilonova. Now, one of the things that we're doing is, instead of waiting for a gravitational wave detection to trigger optical follow-up, we're trying to do something a little bit different, because although we expect around 10 neutron star mergers per year in TVS, and actually, if you redo the math, you can actually find that we will find, without gravitational waves, just from the kilonova, around 300 kilonova for Rubin. We need to find these by not relying on gravitational wave detectors, because they are not online all the time and they don't reach as deep as our optical detectors. And we have been working with this right now, even if Rubin is not online with CTF. We have a partnership with GRANMA, which is a network of telescopes around the world. And we follow up some candidates of potential kilonova without gravitational wave detections. This is a light curve of one of those objects. Disclaimer, none of them is a kilonova. But we are understanding what are the contaminants: asteroids, cataclysmic variables, supernova. So this is work in progress, and it's very exciting. And we hope that with Rubin, we will scale this up. So I have told you a lot of things today. I'm going to summarize it by, I have shown you the tightest constraints on dark energy from type 1a supernova to date, with 1,500 type 1a supernova. From these constraints from the dark energy survey, we have hints of dark energy evolving with cosmic time. This is very interesting, but there are still hints. Rubin will tell us more about this. I have shown you also the power of Fink. Fink is online right now, ready for Rubin, and it will be indispensable to really pinpoint the most interesting candidates from millions of detections every night to do your science. And you can join Fink if you want, or you can use the data without joining. Both are options, but we always want more voices and understand what the community needs because we can build better tools to maximize science. And the last thing I want to tell you is Rubin is an amazing opportunity. It will really revolutionize the way that we see optical astronomy and transient astronomy in the next decade. And we will be having answers to fundamental questions. Is dark energy a constant? Is it not? What are the extreme physics and origins of these transient events? So with that, I'm going to stop. And if you have any questions, I'm more than happy to answer them here, or you can send me an email at any time.
Thank you very much. Questions? Please raise your hand or unmute, whichever you prefer. So I'll start. So yeah, maybe more specific question first. So with the plot that you showed from Des, where you showed how you were now including the weights of the probability of it being classified as a type 1a supernova. Does that make a significant difference to like the reducing the error budget or improving the constraints over just having say a cut? You just say like I believe these are type 1a supernova and I believe these are not, so I'm not going to include them. How much does this sort of spectrum of probabilities improve the situation?
Yeah, so it won't change like the systematic budget by a lot, but we have found that using the weight instead of a cut is much easier to actually model. What we do is that we do very complex simulations to model the contamination. And if you do a cut, that is a very discrete thing. But the truth is, it may vary as things go by, no? And we tested this with different models, different permutations of the models to see if we make the same cut, how much would it change? And we have found that actually it's easier to model a continuum than something that is
Mm.
discrete. So this is a new way of doing this. We are using a method that is called beams by backprop. BBC, which is beams bias correction. Sorry, I'm thinking of Bayesian neural networks in my head. Uh, so this way of analyzing the supernova is not a covariance matrix because that's very hard when you get a lot of type 1a supernova. Before we use like covariance matrices and invert them. But now when you have thousands of supernova, it's very hard to do that. So we are now doing another method where we actually do a Bayesian analysis, and that analysis includes modeling contaminants, and it's better to model those contaminants using these weights, definitely.
Yeah, that makes sense. Yeah. So, to everyone else, uh, if not, I'll keep going. Another question, which is maybe not interesting. I don't know. It sort of stood out to me when you were showing the sky map of the LSST. Yeah, like the LSST skies coverage. Basically, there were like a few spots which seemed to be getting more attention than the rest of the sky. I was just wondering what that was.
Yes. So it's called the deep drilling field. So in general, the purple we will be imaging that part of the sky twice in a night and then every week around it. Like the observing strategy is still not super mega defined, but it's about this. The yellow ones are what we call deep drilling fields because we will image them every couple of days. So the idea is to get a better sampling of transient events, for example. So these are fields that are very designed for supernova cosmology, AGN reverberation mapping, those type of analysis
Because they
to
have a lot of
really get.
galaxies in them, or
Yes, so these are 9.6 square degrees fields to a depth of 24 magnitude. That's a lot of
But I
them.
mean, do those
Uh,
parts of the sky have more galaxies than any other part of the sky? Is I guess my like why
no, they're extragalactic fields,
yeah
so they are not in the galactic plane, and we have chosen them. One of them has an overlap with Euclid, the other one is Cosmos, the other
uh,
is uh, the Chandra deep
yeah okay
field.
yeah
We have other multi-wavelength data as well to understand it. But the reason why we visit it more is because we want to have that light curve very well populated.
yeah that makes sense.
Yeah.
Um, yeah, this question, Remus.
Um, Yeah, thank you. So, hi, Anais. Thanks a lot for the talk. So my question is, I think I saw it in slide 14. You were mentioning something about contamination. And I think it's a bit related to that pixelated galaxy that you've shown. How do you extract information from something like that? I'm just curious. Do you use something like AI to enhance it a bit, or?
You mean the video I showed you at the beginning with the galaxy?
Yes, yeah, there was a video where it kind of shifted towards the pixel. Yeah, this is the video. Yep.
Yes.
So,
This is actually a real image from the dark energy survey. We just zoomed that
mhm.
in.
So,
This is really data. These are the pixels that we get.
mhm,
We're not enhancing them aside from making the video nice with colors.
right.
Yes.
And you
So
mentioned contamination. What did you mean by that? I must have missed it. Or
Ah, contamination is because we have, when you get the supernova, it can be other types of supernova. It can be a type 1a, but it can also be a core collapse supernova, a star that is very old and the radiation pressure against the gravity collapses and then it blows out. These are other types of supernova. They're also very bright, but they are not usable for cosmology. So that's what I call contamination, is confusing those type 1a with another type because then you wouldn't get distance measurement.
I see. Thanks a lot.
Yeah, no worries.
Uh, okay, well, I'll ask one final one from my side. Well, this is going a bit beyond what you actually spoke about, but of course, the supernovae come up quite a lot in the context of the distance ladder and the Hubble tension, and of course, this is a big deal in cosmology. I don't know how many people believe that supernovae are the culprit, as opposed to anything else, but I just, given that you're working in this field, what can you give some 2 cents about the role of supernovae in terms of the Hubble tension or the potential role in that. If you think if there's something hiding, some systematic hiding is going to be on this side rather than anything else.
Yes, so this is a very controversial topic. So to give you a little bit of context for those that don't know about the Hubble tension, basically not a high redshift, but if you go here, like up here in redshift, can you see my mouse?
Yeah.
Yes. So we have a Hubble diagram, a local Hubble diagram that is mentioned, it's measuring the Hubble constant. Now, the Hubble constant for high redshift people like me, it just means a shift. It's a constant. We don't care that much about it. But the problem is that when you go to CMB, which is all the way to the right, very far away in the universe, and you extrapolate what the Hubble constant should be, or when you measure it directly using type 1a supernova, you get a different answer. Now, supernova people will tell you that we understand type 1a supernova pretty well, enough that it's not the culprit, while the CMB people will tell you the same. Now, one of the tests that we have been doing, actually, I'm not part of this, I don't do Hubble constant, but one of the tests that the community has been doing is trying to change how you calibrate those type 1a supernova using Cepheids, stars, using different probes to measure that Hubble constant at very low redshift. And until now, all of them agree. So what's interesting about this is that this may mean that there is some physics that we don't understand in our models. So the models that we're using are need to be improved. Now, some people may ask me, well, now that we are finding this dark energy evolving with cosmic time, does this explain the Hubble tension? Because this high redshift extrapolating to low redshift, and it doesn't. To make both measurements agree, we would need like a dark energy evolving with cosmic time in a value that we cannot find with our data. So still a mystery. This is a very political answer and very hard to say because we don't know what this is happening. But it's a very interesting physics. Like, why are we finding something in the early universe different than the local universe?
But you don't think that like you were talking about, there's this issue about you don't know what the progenitors of many of these supernovae are. You don't that the fact that understanding is not known at the moment is not going to be the thing which resolves this problem, do you think?
No, it won't.
Yeah.
Uh, our uncertainties in the distance measurements due to this lack of knowledge wouldn't explain the
Yeah.
difference in the H naught measurement.
Good. Okay, so last chance for anyone else. If not, so thank Anais again.